Dr. Ranjani Parthasarathi is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on computer architecture. So, in the previous class, we were looking at how a control unit can be designed. We have looked at many of the basics that are required for ALU design and so on. So, now we are into control unit design. So, what we have specifically looked at in terms of control unit design is we try to identify the different elements that are required for the control of the various functional blocks that we have, so that the different instructions can be executed. So, how do we go about doing this? We basically looked at a simple set of instructions and try to identify for executing those instructions what will be the different functional units required and what will be the sequence in which those functional units have to be connected up together, so that we are able to come up with a full, what we call as a full data path. Okay, we looked at different data paths for different instructions. So, what we are going to do now is look at that a little bit more of detail and try to understand how a full control unit design actually looks like. Okay, so this is what we are trying to do today. So, the topic for today therefore is more details on how the design has to be done, and we will also try to address some performance issues. So, this is the picture that we kind of stopped with in the previous lecture. So, where we said we have a full data path that is specified. You can see that we have all the pieces that we want here. Remember all these things. This is the PC, the program counter, which feeds the address to the instruction memory, right. So, from the instruction memory you have the instruction coming out, the data coming out over here, which goes as input to specify the values that will have to go into the read registers. This is our register file. So, register file, remember, will have three register values specified: read register value, read register 2 and the write register number. These are the register numbers, and the data will come out of the read data 1 and read data 2. As control will be specified to specify whether it is a read or a write operation. If it is a write operation, the right data will have to be given over here. Okay. So, these are with respect to register file. Now, remember, this adder is there for the purpose of adding the value of 4 to the PC value, and if it is a jump instruction and further addition that will be done, which will be the offset that will be added to the PC. So, the offset will come from the instruction itself. So, that is sign extended added to the value coming from here. So, one of these two will be chosen as input to the PC. So, either the sequential address or the target address. So, that control, again you can see that there is a signal here which shows that there is a control that will have to be specified, which will specify whether it is this address or this address that has to be loaded to the PC. Then this is our ALU. Again, ALU input can come directly from the instruction if it is, for instance, an address calculation, or the value would come from the register. So, one register value comes directly, another register comes either directly or the value from the instruction is given here after sign extension. Remember, the sign extension was something that we added, and then this value comes as the input to the ALU. So, the ALU will do the job of adding the two and adding or subtracting or whatever. So, that will be specified by means of this control signal called the ALU operation here. Okay. And the output of the ALU, it may be an address if it is a memory operation. So, that goes as the address, okay, or it has to be stored into to a register. So, in order to store it into a register, so either that value or the data which is coming from the memory, if it is a load operation, okay, these two values, one of these two will be again selected by means of a multiplexer, and that value will be written back into the register file. Okay. So, again remember, see that we are having one more control signal here, either memory or register, which is the one that needs to be specified here. So, memory read is another control signal here, memory write is another control signal here, and so on. Okay. So, this is the full data path that we have come up with. Now, you can see that there are so many different control signals that we talked about here. So, the question therefore that comes up is, how do I generate these control signals? And in terms of this design of the data path itself, there are a few things that we need to consider. What we have right now assumed is that for this design, the data path does the entire instruction in one clock cycle. That has been our assumption. Okay. So, each data path element therefore can only do one function at a time, so which is why we have used separate instruction and data memories in this case. And of course, remember this, we have used multiplexers wherever alternate data sources are used for different instructions. Okay, this is what we have. Now, let's look at our R type, that is a register type instruction along with the load store data path. This is what we have, and see how these different control signals can actually be derived. So you can see that if I am just looking at a simple R type and load store data path, I am not looking at the jump instructions. Just for these type of instructions, what are the different control signals that we need to generate? So what are the control signals we will need to generate? You will specify whether you need to do a register write, otherwise a read will be done, and you need to specify what is the source for the ALU, whether it has to come from here or whether it has to come from the instruction, and then what is the ALU operation to be done, and then with respect to a load store, whether if it's a load, a memory read has to be generated, store memory write has to be generated, and then the control for this mux has to be generated. Okay, so let's see how this information can be obtained. So the ALU control, we said a 4-bit value can be used. So how do you decide that? You can have just a 4-bit value specified here, and depending on the value that you have here, the function can be specified. So if it's a load or a store, the ALU, what is the ALU expected to do? It's expected to do a add operation. So the function that needs to be used is an add operation. If it is a branch type instruction, remember we will use the same ALU for subtracting, to find out, for instance, if two registers are equal. We are talking about implementing a branch on equal instruction. So what is a branch on equal instruction? You compare two registers, check whether the value is 0. If the value is 0, it will branch. So we need to do a subtraction in order to do that comparison. So we will use the ALU for doing the subtraction. So this is what we already decided. So the ALU therefore will be used for a branch to do a subtract function. So this f that we are talking about here is the function that the ALU has to implement, and that function you can see is dependent on the instruction that we have. If it is a load or store instruction, f will have to be add. If it is a branch instruction, f will have to be subtract. And if it is an arithmetic or logic instruction, so then what arithmetic or logic operation needs to be performed would have been specified in the say for instance what is called as the function field that you will have in the instruction. So depending on that, this ALU control will have to be generated. So for instance, if we have fixed, for instance, 0000 is AND, 0001 is OR, 0010 is an add, 0110 is a subtract, and so on. So if you have fixed these functions and the corresponding ALU controls, then this control will have to be generated based on the information that is available in the instruction. So if we assume that 2-bit of the ALU operation is derived from the opcode, what is the opcode? Remember, this is our part of our instruction which tells us what is the operation to be performed. We can add some combinational logic which can be used to derive the ALU control. For instance, let's say load word has an ALU op value as 00. So from here, if it's a load word, the ALU function that needs to be done is add. Okay, so 0010 will be the control that needs to be derived. So if it is a store word, ALU operation will be, let's say these two bits will show it's 00. It's a store word operation, and then now again need to do an add. So the same ALU control will be 0010. If it is a branch or unequal, ALU opcode, this code will be 01, which indicates a branch equal. ALU function will be subtract, so 0110 will have to be generated. If it's an R type, then your ALU operation here will be 10, and depending on whether it's an add or a subtract or an AND or a OR or a set on less than, these different function input will be specified in the instruction itself. So based on this function value, I identify what is the add function and generate the corresponding ALU control. So what do I require for this ALU control? Therefore, I require the opcode information, I require this function information. From of course the opcode, I am looking at it in terms of these 2 bits called the ALU OP. ALU OP 2 bits plus the 6 bits coming from the function field. Both these fields are available in the instruction register. So these 2 fields if I take, and I can generate a combinational logic which will give me output, which will output this ALU control bits for me. Okay, so this is how we will develop the ALU control signals. Okay, so let's look at how that is now derived. As I said, the control signals will be derived from the instruction, right? So let's look at this R type instruction. So the R type instruction has this format. This is used for all register type instructions. So you have some value which is specified here, say the value is 0, and then a source register, another source register, okay, 2 source registers are specified, RD will be the destination register, and then there is a shift amount and a function field that is specified here. So this is the format of an R type instruction. Now from this R type instruction, if it is a AL arithmetic logic instruction, let's look at what is the information we can derive from here. Okay, so this field RD will give me the write for the R type, okay, and similarly this RS and RT, these will directly give me the register numbers for doing the read operation. So you can see that R type information, almost everything is explicitly available in the instruction. I just need to pick these correct bits from this 32-bit instruction that I have. So bit number 21 to 25 will give me one source, bit number 16 to 20 will give me another source, bit number 11 to 15 will give me the destination register number. Okay, all this I can pick directly from here. Now if it is a load or a store instruction, say we have a slightly different format. So you will have two registers specified, RS, RT, and then the offset. The offset is available here in this address. Okay, so this address bits, the 16 bits, now remember they have to be sign extended and then added. So this 16 bits I will take from here and give it as the input to my sign extension logic. Similarly, if you look at a branch instruction again will have this register RS which is to be read directly, and then this RT field which will be read again. Okay, and then the address again will be specified here. Again this address will have to be sign extended and added. So if you look at these fields, I can just divide them up into this 1, 2, 3, 4, 5, 6 in this case, and 4 fields in the case of load, store and branch. So you can see that this RS register is always read. Okay, of course the first 6 bits, 26 to 31 gives me the opcode, 6 bits, and then 21 to 25 always gives me the value to be read. Now this value here, okay, the next 5 bits which specifying the next register address, it's a read address except for a load operation. Okay, because when you load, value which is retrieved from memory has to be stored. Okay, so except for load operation, this always gives you a value which needs to be read. Okay, and the RD for all register type operations, this is the value which needs to be written, and again for a load operation this RT will be the value that needs to be written. We just saw that. Okay, and this address field in both, whether it is a branch instruction or a load store instruction, this 16 bits will have to be taken, sign extended and then added. This is the information we can derive from the instruction itself. So that is, we have encoded the instruction in such a way that this derivation becomes easy. So this is how we derive it. So once you have derived this, so now we can see how the input to the control unit will go. Okay, so if you look at this, let's see what we have. So from the instruction, remember the rest of the things are the same. This piece here in the center is our new control that I have added now. How do I look at the data coming from the instruction memory? The instruction comes, which is a 32-bit data. Okay, so 0 to 31. So you can see that 0 to 31 data I take, right, and that most significant bits 26 to 31 which gives me the opcode, right, that goes as input to the control unit. Okay, I put one control unit here, and then those the bits 21 to 25, remember, which correspond to that RS which is always gives me the read register 1, that is given over here. Okay, and then the next RT bits, okay, bits number 16 to 20, which will be either a read value or a write value. Okay, whether it is a read or a write will now depend on whether it is a load instruction or whether it is any other type of instruction. So that information now will come from the control unit. Okay, it will normally go as a read register. If it has to go as a write register, then I have to choose between whether it is this value that's a write register or instruction or the instruction bits 11 to 15 which will give me the write register number. So choosing between these two is done again by means of a mux. Okay, and that control is generated from here. Okay, so you can see that from these bits, and again of course the last 16 bits are given for the sign extension. So we have seen how from the 32 bits the different pieces can be split and used for the control. So we will take a short break and come back and look at the different signals generated from the control unit. Welcome back after the break. So we were just looking at the data path and how the control signals can be derived, control information can be derived from the instruction itself. If we look at this picture that we were just taking a look at, so we saw how from this 32 bits, the bits which specify different pieces of information are split and given to the various control unit and to the actual inputs of the register file. Okay, so this is what we have seen. So now let us look at what more we need to decide. So we said that if to the ALU, we need to specify what is the ALU control information that has to be, we have to specify the operation that needs to be performed, whether it is an add or a subtract or the 4 bits that we need to identify. So how do we do that? So that is identified again by means of the ALU operation information. Okay, and we will also use a few bits from the instruction, the function bits that we have. So remember this picture here. So this function information here will be used to determine what is the type of instruction that needs to, what is the type of ALU operation that needs to be carried out. So this function bits therefore has to be given as input over here. So you can see that the 0 to 5 bits which are there from in the instruction also come as input to the ALU control, in addition to the control signal derived from this control unit from the opcode, which says that it is an ALU operation. Okay, so a combination of ALU operation and this 6 bits, these two will be used in a small control block over here to determine what is the actual ALU operation that needs to be performed. From the control unit, based on the instruction type, you will identify whether it is a branch instruction that needs to be it's a branch instruction, in which case you will generate a control for the branch logic, and then if it is a load, you will be generating this memory read signal which will come to the data memory here. Memory to register, if it is a write operation, then you will be generating this control for this mux over here, and then of course we saw the ALU operation here. Memory write for a store, and then what is the ALU source? If it is a load or a store memory instruction, then we know that the value will have to come from the sign extended part, otherwise it will come from the register. So depending again on the type of instruction, the signal can be generated, okay, and then a register write operation will be generated from the control logic. So for whatever we have looked at just now, so with these control signals which is generated from this control logic, you can have the complete control setup. So what is important therefore is how do I actually come up with this designing this control logic? Of course there are many different types of mechanisms used for that. A very simple and fast mechanism would be what is called as a hardwired control, which means I just specify that these are my inputs, these are the outputs, and come up with a logic, combinational logic. Okay, you can just look at it as a huge truth table and design the combinational logic for doing this. Okay, so we will assume therefore that we have a combinational logic which will allow us to come up with this kind of a control signal. Okay, so that will complete the design of this control unit. Okay, we have looked at an R type instruction, okay, and seen what are the different control signals which are generated for that. Let us first look at the R type instruction, and from this control signals that we just generated, we will see which are the ones that will actually flow. So you can see that for an R type instruction, so the ones that we have, the blocks that are highlighted, you can see that this block and this block are not highlighted. Okay, so which means these are really not used when you have an R type instruction, which is used only for a register based ALU function. So in an ALU function, you can see what is happening here. The control will come from here. Okay, these are the blocks that will be used. The output from here, okay, this output here will flow through this mux, and that output will be written back to the register. Okay, so you can see which are the functional units which are active, and the ones that are active are controlled by the control unit. Similarly, if you look at a load instruction, you can see that when I have a load instruction, look at the function units which are active now. ALU will be active, ALU control is active, this mux becomes active because you are choosing between register or this value. The memory becomes active, okay, memory unit is active, and you are doing a read operation here for a load. That read path, that is activated, okay, the write path is not activated, and then this mux is activated so that the value is written back. Now we will look at a branch instruction, the branch on equal instruction, and see how the control signals have to be generated for the branch on equal instruction. So branch on equal instruction, remember what do we need to do for this? We have to specify the ALU operation as subtract, because we need to subtract the two values. The values that will come are from the two registers. So you can see that you will be choosing read data 1, read data 2 from here. So that control will be set up, and that output will go here. Okay, and of course the sign extension logic will also be enabled because we need to get the offset from the instruction. So the offset, which is 16 bits, will be sign extended, and that will come as the input to this special logic that we have here. Okay, so this logic here, which is shift left and so on. So this shifted input will be added to the PC value which is coming from the PC plus 4, and this target address which is calculated, we have now either choose this target address or the original PC value depending on whether the condition was met or not. Okay, branch on equal condition. How will I know that the condition is met or not? That I will know from the output of the ALU. If the two registers were equal, when I did a subtract, the 0 signal will be set. If the 0 signal is set, and if it is a branch instruction, then I will use that as the control to choose whether I need to choose the target address or I need to go to the sequential address. So if the value is 0, then I will go to the target address. If the value is 1, I will go to the branch. If the value is 0, which means that they are equal, I will branch. If it is not a branch, that means I will go to the sequential instruction. So that control again will be selected in this multiplexer by this kind of a signal. So you can see we added one AND gate here to do that. Similarly, this control unit and this ALU control logic will be full of such logic gates in order to come up with this. Okay, so this is how the different operations are carried out using this kind of a enabling of different elements in the data path. Now, when it comes to implementing jumps, we saw how a branch on equal is generated. What about a plain jump? That is, it's an unconditional jump. So, when an unconditional jump is given, so what will be the piece of information in our instruction? There are only two pieces of information. One will be the opcode, which specifies that it is a jump, and the other is the address to which we need to jump. So, this is an absolute address which is specified. So, jump will assume, gives us word addresses. So, what do we need to do? We need to update the PC with a concatenation of top 4 bits of the old PC with the 26-bit jump address. So, jump address we assume is given here. This we will add to this. So, there are only 26 bits given here. Okay. So, what we do therefore is the top 4 bits of the old PC are added along with this 26 bits along with a 00 extension, so that you are able to generate a 32-bit to which you need to jump. Okay. So, what we need therefore is we need an extra control signal which is decoded from the opcode. So, if you look at this, so you see what is the extra thing we are adding now. So, there is a 00 that is happening here, right, which is basically shifting this 26-bit jump address left by 2 positions. So, this shift you can see is implemented here by means of a shift left by 2. So, what is happening here now? So, now you can see that the 0 to 31 instruction bits that I have, 26 bits out of this 0 to 25 comes as input to the shift left by 2 logic. It gets shifted by 2 positions. Okay. So, this now becomes a 28-bit data, and I am also concatenating this 28 bits with the top 4 bits of my PC address, okay, which gives me the 32-bit address. So, now look at this. So, this value also will have to come as the input to the multiplexer. So, now that is, I am actually now adding one more multiplexer. Okay. So, we already had a multiplexer here. Now, what I have done is I have added one more multiplexer. Of course, you could have combined these two multiplexers as a single multiplexer. That is what would normally be done. But just for our ease of understanding, when we are adding one more logic, I am just adding one more multiplexer here. So, I add one more multiplexer here, which will choose on whether it is a conditional branch or an unconditional branch. So, the control for this therefore will come from the control logic, which says that if it is a jump, then you choose this. Okay, and then it will take it from this jump address instead of taking it from the address which is coming from this multiplexer here, which was used to identify the target address. Okay. So, with the jump added, you can see that this will be the total data path that we have, and when it is a jump operation, this path is the one that will be highlighted, or this is the path that will be selected. Okay. So, this is what happens. What we have assumed in this entire discussion therefore is that this whole thing takes place within one clock cycle. Okay, that was our assumption. So, within one clock cycle, all these things will get done for every instruction. So, you can see that because different data paths actually are highlighted for each different instruction, the time taken may vary for each instruction may vary. But therefore, if we assume that the whole thing takes place in one clock cycle, our assumption therefore will be whichever is the longest instruction, that will determine the size, that will determine the duration of the clock cycle. So, that would be our assumption for the simple design. So, which brings us to what will be the performance issues that we need to look at. Okay. So, as we said, the longest delay will determine the clock period. Okay. So, which will be the critical path here? You can see in our case, the critical path will be for a load instruction. Why did we say load instruction? So, remember, for a load instruction, the different units that have to be touched are these: instruction memory first, then the register file has to be read to get the address, then ALU for doing the memory address calculation, and then data memory has to be accessed to actually fetch the data, and then the register file again has to be accessed in order to write the data back into the register. Okay. So, you can see this is the kind of the longest path that we have. So, we say that this is our critical path. So, this critical path is what will determine our clock period. Now, in this kind of an architecture that we looked at, we are not looking at the feasibility of varying the period for different instructions. Okay. So, we will assume therefore that whatever is the longest delay, if the longest delay was load instruction, so load instruction will be looked at as the determining factor for determining the clock period. Okay, as the main factor for determining the clock period. Now, if I want to improve the performance further, there are various other techniques that we use. One such technique is what is called as pipelining. We will look at this pipelining in the next lecture. To summarize, what we have looked at in today's lecture is basically how this control unit can be designed. Okay. So, we have seen that the control unit design is based on the instructions that we choose. So, of course, we have taken a very simple set of instructions here. We looked at only a very small set. We looked at a load, a store, a few register operations and two types of branches, a conditional branch and an unconditional branch. But this set of instructions kind of suffices for us to understand the complexity of the control unit design. Okay. And in fact, it gives us many of the ideas that are required for doing control unit design, because this class of instructions almost covers different types of instructions that we are likely to encounter. Okay. So, we looked at how the logic needs to be identified. Okay. So, the logic required we identified based on the instructions again. Okay. So, then of course, we also looked at identifying the data path for the different instructions, and we saw how the control information can be derived from the instruction. Okay. Not only from the instruction directly, but also from different pieces of information that come out when the instruction is actually getting executed. That is, as output of some of the units, the output of some of the units also give us some control information. Okay. So, we use the information coming from the instruction, the opcode and the other fields that we have, and then also some information which comes from from the different functional units when it is actually getting executed, and we use a combination of these two to derive the control information. Of course, what we have also looked at is we have assumed a very neat encoding technique, so that it becomes very easy to take out the different parts of the instruction separately, so that we are easily able to identify what we really need. This actually emphasizes for us the need for a very neat encoding. We actually used a very neat encoding here, so that makes the job easier for us. So, once the job is easy with the encoding, we can then easily derive the control information and develop the design the control unit. We also looked at the importance of identifying the critical path, because this will tell us how much time it actually takes for an instruction to be executed. Okay. So, based on this, you can actually you are now in a position to design small control units for such small processors that you look at. Okay. So, a set of questions therefore now for you to review the matter today. Question number 1, what are the pieces of information we get from the R type instruction? So, remember we have looked at different types of instruction. So, for the R type instruction, what are the pieces of information we get? Question number 2, which bits are used for deriving the control bits in a load instruction? Question number 3, what is the difference in the control data path for a jump and a branch equal instruction? Question number 4, design the combinational logic required to control the sign extension logic block. So, here I am asking you to design the combinational logic. Okay. It is a very simple piece of logic, some AND gate, OR gate, whatever, just figure out what you need to do for that. Question number 5, what is meant by critical data path? Thank you.